Good people, welcome to JJ Tech Tutoring. In today's video, I will be taking you guys through separately excited brush DC motors, right? So now I will quickly take you through these circuits and also explain the formula for you. Then I go and do tutorials for you, as I always want to teach you how to go around with questions, because I assume you know the theory part. Right now, separately excited. So that simply means that the field winding gets power from an external DC voltage, right? So now we've got two machines here. We've got a generator, we've got motor, right? So what are the difference between the two? So a generator actually converts mechanical energy to electrical energy, and motor converts from electrical energy to mechanical energy, right? So as you can see, the armature current here for generator, it actually goes outside to can deliver electricity, right? So it all starts here from mechanical energy, right? So it starts with the rotation here, then from there the current moves from here to the load. So as it does that, it is actually going to bring out the output of electrical, right? So when we talk about motor, this armature current comes inside to can power the motor here, and it starts rotating, and then as it's rotating, it is forming or making mechanical energy, as simple as that. So there's a power here that actually push the current from the load to the winding, right? And then from there, when it gets here, it actually makes mechanical energy. So which is why we say the difference between motor and generator, it's actually the direction of the current, right? So that's the main difference between them, the direction of the current. So the other current goes inside, the other current goes outside, right? Now, yeah, as I've said, current, the direction of the current is actually for generator out of the armature, and for motor into the armature, right? So as you can see, the voltages here, the voltage is here. So this one is just back EMF, it's V terminal minus the armature voltage drop, right? So generator technically works for power generation, right? For wind and hydro and thermal power plant, right? Now for motor, you know, it's it is mostly used with electrical vehicles and other machines, right? So these are the formulas, right? So these are the formulas, and then how we go around this, right? Then now I'm going to be answering questions for you, as I am here for that, right? So problem one, it's always easy. Problem one, right? Now the terminal voltage of a separately excited brush DC generator. So now we know which formula we're going to use now that we have this name, right? With a constant excitation is equals to 250 volts, right? So this is our terminal voltage. So determine the EMF induced and the power developed when supplying a load 250 kilowatts, right? So this is our power. It's in load, so you bear that in mind. The armature resistance is 0.012, and the total constant drop at brushes is 2 volts, right? So this is another voltage drop that is in the machine, or that is in the circuit, that we need not to forget when we are calculating the total EMF. We need to include that, right? Now, what is our armature current? This one with the voltage, the generator, this one goes to the load, right? So it somehow acts as a load current because it goes to the load. And then what we have again, we have the power that is in the load, right, which is 250 kilowatt, that is in the load. And then we have terminal voltage, that is 250 volts, that is in the load. So basically all these three things are in the load. That means they can use each other to can find each other, right? So now power is equals to VI, right? Now we can say armature is equals to P over V, which is 250 K divided by 250, right? So that means our current is K, so it's 1000 amperes, right? It's 1000 amperes, right? So this is our current. Now, what is our formula? Our formula for induced EMF is E generator is equals to terminal voltage plus the voltage drop of the armature. Then, now that we have this drop, constant drop that is here, so we can just add it with another color, V drop, that is introduced, right? I am well aware that the only formula that you are introduced to is this one, but then now that we have the drop into our machine, we have the drop into our circulation, or the generation of electrical energy from mechanical energy, then we have to include it, because this is the voltage that is also lost in a process of converting from mechanical energy to electrical energy, right? Now we've got 250 plus 1000 multiplied by 0.012 plus 2, and EG is equals to 250 plus 1000 times 0.012 plus 2. Then the answer is 264 volts, right? So let us go back to the question again and understand what is it that is needed, and then are we done answering the question. A terminal voltage of a separately excited brush DC generator with a constant excitation is equals to this. Determine an EMF induced and the power developed, right? The power developed, right? So power developed is equals to E generated EMF multiplied by the armature current. So it's gonna be 264 multiplied by 1000. Then it's 264 million. 264 millions watts. So it's 264 kilowatt, right? So the power developed is always greater than the induced EMF when we are dealing with a generator, right? So the EMF that we get should be smaller than the EMF that we have. So the induced power, right? Now going to the second question, because now I think we're done with this one, right? So a shunt brush DC machine supplies and takes 500 amperes at 500 volts when running as a generator and a motor respectively, if its armature and shunt field resistance. So if it's armature and shunt field resistance, so that means now they spoke about respectively, they spoke about the motor, so that means this one is RA, this one is RF. Clear, right? Respectively compute the EMF and the power developed when running as a motor and as a generator. So now we know that a shunt brush DC machine can work as a generator and as a motor. The difference is the direction of the current, right? Because in generator the current flows out of the armature, and in motor it flows into the armature, right? Now let's start with the generator. Let's start with the generator, right? Now we have got a supplied current, so we have IL, so current load is 500 amperes. We have got the terminal voltage of 500 volts, right? Now what we need, we then need IF and IA, right? Because this is a shunt brush, so IL is not equals to IA. IA and IL and IF are only equals in a series, which we're gonna do that kind of equation soon, right? So first thing first, we need to then find IF. IF is equals to voltage divided by resistance, Ohm's law, right? So because this one, it's a terminal voltage and it's connected across or in the load, so actually it is actually the same voltage with the field voltage, right? So it's gonna be 500 divided by 125, right? So IF is equals to IF is equals to 4 amperes, right? So IL is 500. So IA is equals to IL plus IF, right? So that's the formula, right? Now IL is equals to 500 plus 4. So 504 amperes for the armature current, right? Now from there, we've got the armature current, we've got the armature resistance, then we can be able to find our EMF for the generator, which is EG is equals to VT plus IARA, which is equals to VT is 500 plus 504 multiplied by 0.02, right? Which is 500 plus 504 multiplied by 0.02, which is equals to 510.08 volts, right? So this is the generated volt. Now, what do we need again? Then the question spoke about power developed. So how do you find power developed? So power developed is equals to EG multiplied by IA. So 510 multiplied by IA is 504. So it's 25,780.32, which is 25.71 kilowatt. So this is the power developed. That is the power developed, right? Now let's deal with motor. Right now, to the side of the motor, then we have to then solve the question now focusing on motor, right? Now a shunt brush DC machine supplies and takes a 500 amperes at 500 volts when running it as a generator and as a motor, respectively, if its armature and shunt field resistance are 0.02 and 125 ohms, respectively. Compute the EMF and the power developed. So now we are going to look for the back EMF and the power developed of a motor, right? Now our formula is terminal voltage minus armature drop, right? So what is it that we have? We have got equals to minus IF. So our armature current is equals to I load minus I field, right? So what is it that we don't have? I field. So I field is equals to V terminal divided by R field, which is 500 divided by 125, which is equals to 4 amperes, right? Now IA is equals to IL is our 500 minus 4, then it's gonna be 500 minus 4, then it's going to be 496, right? 496 amperes, right? Then we're gonna then find our counter EMF or our back EMF, which is equals to terminal voltage minus armature drop. Then it's 500 minus 496 multiplied by 0.02, which is equals to 500 minus 496 multiplied by 0.02, then it's gonna be 490.08 volts, right? So one thing you should know about the motor is that the terminal voltage is always greater than the back EMF, always. But when it comes to generator, terminal voltage is always smaller than the induced EMF. That's it, right? Then we are going to look for power developed. Power developed is equals to back EMF multiplied by